ground ring, sometimes called a ground loop, is a conductive pathway that links the grounding electrodes of a building or structure to the earth. The purpose of a ground ring is to offer a low resistance route for electrical current to flow in scenarios such as electrical faults, lightning strikes, or other electrical surges. This mechanism is designed to safeguard the building, its occupants, and its equipment from electrical hazards like shocks and fires. The theory underpinning a ground ring relies on the principles of electrical potential. When an electrical current traverses a conductor, it generates an electrical potential difference, also known as voltage, between the conductor's ends. The magnitude of this voltage difference is directly proportional to the current strength. In the context of a ground ring, the electrical current moves from the grounding electrodes into the earth. The earth acts as an extensive electron reservoir, thus maintaining a relatively small voltage difference between the grounding electrodes and the earth. This minimal voltage difference enables the current to flow readily through the ground ring without substantial voltage drops. The resistance within a ground ring is dictated by the conductor's length, size, and material composition. A shorter ground ring utilizing a larger conductor exhibits lower resistance compared to a longer ground ring using a smaller conductor. The conductor's material also influences resistance, with copper outperforming aluminum and steel in conductivity. The effectiveness of a ground ring depends on several elements. Firstly, the size of the ground ring. Secondly, the number of grounding electrodes deployed. Thirdly, the depth at which these grounding electrodes are buried. Fourthly, the properties of the soil surrounding the grounding electrodes. A more extensive ground ring, incorporating more grounding electrodes installed at greater depths, delivers a reduced resistance path for electrical current. This, in turn, bolsters the protection of the building and its inhabitants against electrical shocks and fire incidents. Now, let's elaborate on each of these aspects to provide a clearer understanding of how a ground ring functions and how its effectiveness can be optimized. Firstly, the size of the ground ring is a critical factor. A larger ground ring effectively increases the surface area in contact with the earth. This larger contact area reduces the overall resistance of the grounding system, facilitating a more efficient dissipation of fault currents. The size should be determined based on the building's footprint and the anticipated fault current levels. It's generally recommended to encircle the entire building foundation to maximize coverage. Secondly, the number of grounding electrodes significantly impacts the ground ring's performance. Multiple grounding electrodes provide parallel paths for fault current to flow into the earth. This redundancy reduces the overall impedance of the grounding system, enhancing its ability to handle large surges. The spacing between electrodes should be optimized to ensure uniform current distribution and minimize the potential for localized voltage gradients. Local electrical codes and standards often specify the minimum number of electrodes required based on the building's size and occupancy. Thirdly, the depth of the grounding electrodes is another key consideration. Deeper electrodes typically reach soil layers with lower resistivity as the moisture content and mineral composition tend to be more stable at greater depths. This lower resistivity reduces the electrode-to-earth resistance, improving the grounding system's effectiveness. The depth should be chosen based on soil conditions and local regulations, with deeper installations generally providing better performance, especially in areas with dry or rocky soil. Fourthly, the type of soil plays a crucial role in the overall effectiveness of the ground ring. Soil resistivity varies significantly depending on its composition, moisture content, and temperature. Soils with high clay content and adequate moisture tend to have lower resistivity, while sandy or rocky soils often exhibit higher resistivity. It's essential to conduct soil resistivity testing to determine the optimal depth and spacing of grounding electrodes. In areas with high soil resistivity, soil enhancement techniques, such as adding bentonite clay or ground-enhancing compounds, may be necessary to reduce the electrode-to-earth resistance. Furthermore, the material used for the ground ring conductor is of paramount importance. Copper is generally preferred due to its excellent conductivity and corrosion resistance. However, copper can be expensive, and in some cases, aluminum or copper-clad steel may be used as alternatives. The conductor size must be sufficient to handle the anticipated fault current without excessive heating or voltage drop. Electrical codes typically specify the minimum conductor size based on the size of the service entrance and the available fault current. The connections between the ground ring conductor and the grounding electrodes must be made with high-quality connectors to ensure a low-resistance, reliable connection. These connections should be properly protected from corrosion to maintain their integrity over time. Regular inspection and maintenance of the ground ring are essential to ensure its continued effectiveness. This includes checking the condition of the conductor, connections, and grounding electrodes, as well as verifying the soil resistivity and making any necessary repairs or adjustments. The ground ring should also be tested periodically to measure its resistance to earth and ensure that it meets the requirements of applicable electrical codes and standards. In addition to protecting against electrical shocks and fires, the ground ring can also help to reduce electromagnetic interference (EMI) and improve the performance of sensitive electronic equipment. By providing a low impedance path for high-frequency currents, the ground ring can minimize the amount of noise that is coupled into electronic circuits. This is particularly important in telecommunications facilities, data centers, and other environments where reliable operation of electronic equipment is critical. When designing and installing a ground ring, it's important to consult with a qualified electrical engineer or grounding specialist to ensure that the system meets the specific requirements of the application. They can perform detailed calculations, conduct site surveys, and provide recommendations on the optimal size, configuration, and materials for the ground ring. They can also help to ensure that the installation complies with all applicable electrical codes and standards. Now let's discuss the specifics of 250.52 FR of the National Electrical Code, which pertains to ground rings. This section outlines the requirements for using a ground ring as a grounding electrode. Firstly, the ground ring must encircle the building or structure. Secondly, it must be directly buried in the earth. Thirdly, it must be at least 2.5 feet below the surface. Fourthly, it must consist of at least 2 American wire gauge copper conductor. The requirement that the ground ring encircle the building ensures that it provides a continuous, low impedance path for fault current to flow around the perimeter of the structure. This helps to minimize voltage gradients and protect against step and touch potentials, which can be hazardous to personnel. The direct burial requirement ensures that the ground ring is in direct contact with the earth, providing a low resistance connection to the earth mass. The minimum depth requirement of 2.5 feet helps to ensure that the ground ring is in contact with soil that has a relatively stable moisture content and temperature, which can improve its performance. The minimum conductor size requirement of 2 American wire gauge copper ensures that the ground ring has sufficient ampacity to carry the anticipated fault current without excessive heating or voltage drop. It's important to note that the requirements of 250.52 FR are minimum requirements, and in some cases, it may be necessary to exceed these requirements to achieve the desired level of grounding performance. For example, in areas with high soil resistivity, it may be necessary to use a larger conductor size or install additional grounding electrodes to reduce the overall impedance of the grounding system. The use of a ground ring can be particularly beneficial in situations where other types of grounding electrodes, such as ground rods or ground plates, are not practical or effective. For example, in areas with shallow bedrock or sandy soil, it may be difficult to drive ground rods to the required depth. A ground ring can provide a more effective grounding solution in these situations. In addition to providing a low impedance path for fault current, a ground ring can also help to improve the overall quality of the electrical system by reducing noise and transient voltages. This can be particularly beneficial for sensitive electronic equipment such as computers, telecommunications equipment, and medical devices. By providing a stable, low impedance reference point, the ground ring can help to minimize the effects of voltage fluctuations and electromagnetic interference, improving the reliability and performance of electronic equipment. When installing a ground ring, it's important to pay attention to the details of the installation to ensure that it meets the requirements of applicable electrical codes and standards. This includes properly bonding the ground ring to the building's grounding electrode system, using corrosion-resistant connectors, and protecting the conductor from physical damage. It's also important to conduct regular inspections and maintenance to ensure that the ground ring continues to function properly over time. In conclusion, a ground ring is an effective means of establishing a low-impedance grounding system, particularly well suited for telecommunications sites and other facilities demanding robust grounding for safety and operational reasons. It's imperative to adhere to the guidelines outlined in 250.52 FR and to tailor the design and installation to the specific site conditions and equipment requirements. This ensures a safe and reliable electrical system. Understanding the theory behind ground rings, along with the factors influencing their effectiveness, is crucial for electrical engineers, technicians, and anyone involved in the design, installation, and maintenance of electrical systems. By implementing proper grounding techniques, we can protect people and property from the hazards of electrical shock and fire, and ensure the reliable operation of electronic equipment. Moreover, continuous learning and staying updated with the latest revisions in electrical codes and standards are vital to maintaining the highest levels of safety and performance in electrical grounding practices. The effectiveness of a ground ring is also closely related to the concept of equipotential bonding. Equipotential bonding involves connecting all metallic components within a building or structure to the grounding system. This creates a common ground potential, minimizing the voltage differences between different parts of the system. By reducing voltage gradients, equipotential bonding helps to prevent electrical shocks and ensure the safe operation of sensitive equipment. The ground ring serves as a critical component of the equipotential bonding system, providing a low impedance path for fault current to flow and helping to maintain a stable ground potential throughout the facility. The combination of a well-designed ground ring and effective equipotential bonding techniques provides a comprehensive approach to electrical safety and performance. Furthermore, the location of the ground ring relative to other underground utilities is an important consideration. The ground ring should be installed at a sufficient distance from underground gas lines, water pipes, and other utilities to prevent any potential hazard. The installation should also comply with all applicable regulations regarding the location of underground electrical facilities. Careful planning and coordination with other utility providers are essential to ensure a safe and reliable installation. In addition to the technical aspects of ground ring design and installation, it's also important to consider the environmental impact of the grounding system. The materials used for the ground ring and grounding electrode should be environmentally friendly and comply with all applicable environmental regulations. The installation process should minimize disturbance to the surrounding environment and avoid any contamination of soil or water. Sustainable grounding practices are becoming increasingly important as we strive to reduce our environmental footprint. Regular testing and inspection of the ground ring are essential to ensure its continued effectiveness. The resistance to earth should be measured periodically to verify that it meets the requirements of applicable electrical codes and standards. The connections between the ground ring conductor and the grounding electrode should be inspected for corrosion or damage. Any necessary repairs or replacements should be made promptly to maintain the integrity of the grounding system. Proper documentation of the ground ring installation, including the location of the conductor, grounding electrodes, and connections, is essential for future maintenance and troubleshooting. This documentation should be kept readily available and updated as necessary. Effective communication and collaboration between electrical engineers, technicians, and facility managers are crucial for ensuring the long-term reliability and performance of the ground ring. By working together, these professionals can identify potential problems, implement effective solutions, and maintain a safe and reliable electrical system. In summary, a ground ring is a vital component of a comprehensive electrical grounding system, providing a low impedance path for fault current to flow and helping to protect people and property from the hazards of electrical shock and fire. By understanding the theory behind ground rings, the factors influencing their effectiveness, and the requirements of applicable electrical codes and standards, we can design, install, and maintain grounding systems that provide a safe and reliable electrical environment.